Hello everyone, I'm Rahul Chowdhury, and welcome to our comprehensive course on process anatomy in operating systems. Today we're diving deep into how processes are structured and organized in system memory, which forms the foundation for understanding advanced operating system concepts. Let's begin with our fundamental question. What exactly is process anatomy? Process anatomy refers to the detailed structural organization and layout of processes as they exist in system memory during execution. Process anatomy encompasses the structural organization of processes in system memory, defining how different components are arranged and interact. This organization is crucial because it determines how efficiently programs execute and how securely they operate within the operating system environment. Now let's examine memory organization. When a process runs, the operating system allocates and structures memory in very specific ways. This isn't random. There's a deliberate architecture that optimizes performance and maintains system stability. The core components we'll be exploring throughout this course include four essential sections: the text section containing executable code, the data section for global and static variables, the stack for function calls and local storage, and the heap for dynamic memory allocation. Each serves a distinct purpose in process execution. Understanding process anatomy is fundamental to systems programming, debugging, and optimizing application performance. As we progress through this course, you'll see how these concepts directly impact real-world software development and system administration. Now that we've introduced the concept of process anatomy, let's dive into a fundamental distinction that often confuses students: the difference between a program and a process. This distinction is absolutely critical to understanding how operating systems work, so let's break it down carefully. First, let's talk about a program. Think of a program as your source code after it's been compiled. A program is static. It's just an executable file sitting on your disk or storage device. It contains instructions and data, but it's not doing anything. It's like a recipe in a cookbook. It has all the information needed, but nothing is being cooked yet. Now, a process is completely different. A process is what happens when you actually run that program. A process is the active, living instance of a program. When you click an executable or run a command, the operating system loads that program into memory and creates a process. The process has its own memory space, execution state, and resources. The key differences come down to three main areas: state, memory allocation, and execution context. A program has no state, it's just code. But a process has dynamic state, allocated memory sections, and an active execution context with registers and a program counter. This distinction will be crucial as we explore process memory organization in the upcoming sections. Now that we understand the fundamental distinction between programs and processes, let's examine how a simple process actually executes within the operating system. Today we'll focus on simple process execution, the basic flow without the complexities of advanced memory management that we'll explore later. The first step is process creation and initialization. This is where the magic begins. The operating system takes our static program and breathes life into it. The OS allocates dedicated memory space for the new process, loads the program code into memory, and initializes the process control block with essential information like process ID and initial register values. Once initialized, we enter the instruction fetch and execution cycle, the heartbeat of process execution. This cycle repeats continuously until the process terminates. The CPU fetches instructions sequentially from memory, decodes them to understand what operation to perform, executes the instruction, and then updates the program counter to point to the next instruction. Finally, let's look at the basic memory layout that supports this simple execution model. Even simple processes need organized memory structure. The code segment contains our executable instructions, while the stack segment manages function calls and local variables. This basic layout provides the foundation for process execution that we'll expand upon in the coming sections. Building on our foundation of process concepts, let's now dive deep into one of the most critical memory sections, the stack. This is where function calls and local variables live, and understanding it is essential for systems programming. The stack operates on a LIFO principle, last in, first out. Think of it like a stack of plates you can only add or remove from the top. This ordering is crucial for function call management. Let's examine this visualization. Here we see the main function frame at the bottom. When main executes, it gets its own stack frame containing local variables, parameters, and return address information. When main calls function foo, a new frame is pushed on top. The foo frame contains its own local variables and parameters, completely separate from main's data. And when foo calls bar, another frame is added on top. Notice how each function call creates a new layer, following that LIFO principle we discussed. The stack pointer keeps track of the current top of the stack. As functions are called, it moves up. As they return, it moves back down, automatically cleaning up local variables. Let's review the key concepts. Each stack frame contains parameters passed to the function, the return address so we know where to go back, and all local variables declared within that function scope. Remember, each function call creates a completely new frame on top of the stack. This isolation is what allows recursive functions to work. Each recursive call gets its own separate memory space. When functions return, their frames are automatically removed in reverse order. Now that we've explored the stack and how it manages function calls and local variables, let's move on to another critical part of process memory, the data section. This is where our global and static variables live throughout the program's execution. The data section is responsible for storing global and static variables in process memory. Unlike the stack, which grows and shrinks dynamically, the data section has a fixed layout that's determined when the program loads. First, we have the data section, which contains initialized globals. These are global and static variables that have been given initial values in your code. For example, if you declare int count equals 100, at global scope, this variable and its initial value of 100 would be stored here. Next is the BSS section, which stands for block started by symbol. This section holds 0 initialized global and static variables. When you declare a global variable without initializing it, like int total, it automatically gets placed here and initialized to 0. We also have a read-only section that contains string literals and constants. When you write something like printf, hello world, that string literal gets stored in this read-only area, which helps prevent accidental modification of constant data. The memory layout of these data sections is crucial because it determines how addressing and access patterns work. The operating system sets up these sections with specific memory addresses and permissions, ensuring that initialized data, uninitialized data, and read-only data are properly organized and protected. Understanding the data section helps us see how different types of variables are managed in memory. While local variables live on the stack temporarily, global and static variables have a permanent home in these data sections for the entire lifetime of the process. Now that we've explored the data section for global and static variables, let's turn our attention to another crucial memory area, the heap. The heap is where dynamic memory allocation happens during runtime. The heap structure is designed specifically for dynamic allocation. Unlike the stack, which grows and shrinks automatically, the heap requires explicit management through functions like malloc to allocate memory and free to deallocate it when you're done. The heap grows upward in memory, expanding as your program requests more space. However, this flexibility comes with a cost: fragmentation. As you allocate and free memory blocks of different sizes, you end up with scattered free spaces that can be difficult to use efficiently. This brings us to the management challenges. Memory leaks occur when you forget to call free, leaving allocated memory unusable. Memory corruption happens when you write to freed memory or access memory outside your allocated bounds. These bugs can be particularly nasty to track down. How does the heap compare to the stack we just covered? The stack is fast and automatic but limited in size and scope. The heap gives you flexibility and larger capacity, but requires careful management and is slower to access. Each has its place in effective memory management. The key concept here is runtime allocation flexibility. The heap allows your program to adapt its memory usage based on actual needs rather than compile time estimates. This makes it essential for data structures that grow dynamically, like linked lists or variable-sized arrays. Now that we've explored each memory section individually, let's see how they all work together in a complete process demonstration. This is where everything comes together. Here we have a complete memory layout showing all 4 sections we've studied. Notice how they're organized in the virtual address space from low to high addresses. At the bottom, we have the code section containing our program instructions, starting from low memory addresses. Moving up, the data section holds our global and static variables that we discussed earlier. The heap grows upward from the data section, managing our dynamic memory allocations. And at the top, the stack grows downward from high memory addresses, handling function calls and local variables. Let's trace through a typical execution flow to see how these sections interact during program runtime. Step 1. When the program loads, the operating system initializes the code section with our executable instructions. Step 2. Global variables are created, and the data section gets populated with their initial values. Step 3. When a function is called, a new stack frame is pushed onto the stack, containing parameters and local variables. Step 4. If malloc is called within that function, memory is allocated on the heap for dynamic data structures. Step 5. All these sections interact seamlessly. The code executes, accessing data from all memory regions as needed. Remember, this entire address space is virtual memory. Each process sees a complete private address space, even though the physical memory is shared and managed by the operating system. This gives us both protection and the illusion of unlimited memory. You now have a complete picture of how process memory is organized and how all the pieces work together.